A separately derived system, as defined by the National Electrical Code, is a premises wiring system whose power is derived from a source of electricity that is not connected to the normal supply source, which is typically the utility. In the scenario presented, involving a 480/277 volt 1200 amp service with ground fault protection and a diesel generator feeding two automatic transfer switches, the generator is indeed a separately derived system. Because it is a separately derived system, the neutral must be bonded to ground at the generator location. This is a critical safety measure. If the neutral is not bonded to ground, a phase-to-ground fault will not create a sufficient return path for fault current. Without this return path, the generator breaker will not operate, leaving the fault uncleared and creating a potentially dangerous situation. The addition of a 3-pole automatic transfer switch does not negate the requirement for the generator neutral bond. The neutral bond must remain in place. The installation of a 3-pole automatic transfer switch does not create a second service ground point, provided the neutral is only bonded to ground at the generator. The 3-pole automatic transfer switch simply isolates the generator from the utility source. It does not establish a separate ground reference. To elaborate on the importance of neutral bonding in a separately derived system like a generator, consider the fundamental principles of fault current flow. In a grounded electrical system, the neutral conductor provides a low impedance path for fault current to return to the source. This low impedance path is essential for ensuring that overcurrent protective devices, such as circuit breakers, operate quickly and effectively to clear faults. Without a properly bonded neutral, the fault current may be limited by the impedance of the grounding path, which could be significantly higher than the impedance of the neutral conductor. This higher impedance would reduce the magnitude of the fault current, potentially preventing the circuit breaker from tripping. In the context of a generator supplying power to a facility through an automatic transfer switch, the neutral bond at the generator establishes the necessary reference point for fault current to flow back to the generator in the event of a ground fault. This allows the generator's overcurrent protection devices to quickly isolate the faulted circuit, preventing damage to equipment and minimizing the risk of electrical shock. Now, let's address the concern about creating two service ground points when a 3-pole automatic transfer switch is used. A service ground point is typically defined as the location where the neutral conductor is bonded to ground at the service entrance. In a typical utility-supplied service, this bond is made at the main service disconnect. However, in a separately derived system, such as a generator, the neutral bond is established at the generator itself, not at the automatic transfer switch. The 3-pole automatic transfer switch only switches the 3-phase conductors. It does not switch the neutral conductor. This means that the neutral conductor remains connected to the grounded neutral at the generator, regardless of whether the generator or the utility is supplying power. Therefore, the installation of a 3-pole automatic transfer switch does not create a second service ground point. The neutral is only bonded to ground at the generator, which is the designated point for neutral grounding in a separately derived system. It's important to differentiate between a 3-pole automatic transfer switch and a 4-pole automatic transfer switch. A 4-pole automatic transfer switch switches all 4 conductors, including the neutral conductor. In some applications, a 4-pole automatic transfer switch may be used to isolate the generator neutral from the utility neutral. However, even when a 4-pole automatic transfer switch is used, the generator neutral must still be bonded to ground at the generator. The purpose of the 4-pole automatic transfer switch in this case is to prevent circulating currents between the generator neutral and the utility neutral, which can occur if both neutrals are bonded to ground. In the specific scenario described, one automatic transfer switch is 4-pole with a switch neutral and it feeds a 480/277 volt light safety lighting panel board. The other automatic transfer switch is 3-pole with no neutral and it feeds a motor control center with only 3-phase 480 volt loads. The 4-pole automatic transfer switch used for the life safety lighting panel board is likely intended to prevent circulating neutral currents and to ensure proper operation of the ground fault protection system. The 3-pole automatic transfer switch used for the motor control center is appropriate because the motor control center only serves 3-phase loads and does not require a neutral connection. It is also crucial to consider the implications of ground fault protection in the system. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional connections between a phase conductor and ground. Ground fault protection is typically required for large capacity services, such as the 1200 amp service described. The effectiveness of ground fault protection depends on the presence of a properly bonded neutral. If the neutral is not bonded to ground, the ground fault current may be limited, preventing the ground fault protection system from operating. This could result in a prolonged ground fault, which could damage equipment and create a safety hazard. Therefore, ensuring that the generator neutral is properly bonded to ground is essential for the proper operation of the ground fault protection system. In summary, the generator in this scenario is a separately derived system and its neutral must be bonded to ground at the generator. The addition of a 3-pole automatic transfer switch does not negate this requirement, nor does it create a second service ground point. The neutral bond at the generator ensures proper fault current flow and allows the generators of current protection devices to operate effectively. It is also essential for the proper operation of the ground fault protection system. Understanding these principles is crucial for designing and maintaining safe and reliable electrical systems with generator backup. When dealing with separately derived systems, it's always a good idea to consult with a qualified electrical engineer and to refer to the latest edition of the National Electrical Code for specific requirements and guidance. Furthermore, regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. This includes verifying the integrity of the neutral bond at the generator and testing the operation of the ground fault protection system. By following these practices, it is possible to ensure the safety and reliability of electrical systems with generator backup power. To further clarify the NEC requirements related to separately derived systems and neutral bonding, let's delve into some specific code sections. NEC Section 250.30 covers grounding of separately derived alternating current systems. This section requires that the neutral of a separately derived system be grounded, unless certain specific exceptions apply. The general rule is that if the separately derived system supplies premises wiring, the neutral must be grounded. This is typically the case for generators that provide backup power to a facility. NEC Section 250.30 outlines the requirements for grounding the neutral of a separately derived system. It specifies that the grounding electrode conductor must be connected to the neutral at the source of the separately derived system, which in this case is the generator. The size of the grounding electrode conductor must be determined in accordance with NEC Table 250.66 based on the size of the ungrounded conductors. NEC Section 250.30 provides an exception to the general rule for grounding the neutral of a separately derived system. This exception applies if the separately derived system supplies only equipment and does not supply premises wiring. In this case, the neutral is not required to be grounded, but certain other conditions must be met. However, this exception is unlikely to apply in the scenario described, as the generator is supplying power to premises wiring, including a life safety lighting panel board and a motor control center. NEC Section 250.20b also addresses the grounding of alternating current systems. This section requires that alternating current systems operating at 50 volts or more be grounded, unless certain exceptions apply. This requirement applies to both utility-supplied systems and separately derived systems. The purpose of grounding these systems is to limit the voltage to ground during normal operation and to provide a low impedance path for fault current to flow back to the source. The NEC also provides requirements for the location of the neutral bond in a separately derived system. NEC Section 250.24 specifies that the neutral conductor shall be connected to the grounding electrode conductor at the service equipment or at the source of a separately derived system. This means that the neutral bond must be located at the generator, not at the automatic transfer switch. It is important to note that the NEC is a minimum standard and that local codes and regulations may impose additional requirements. Therefore, It is always essential to consult with the local authorities having jurisdiction to ensure compliance with all applicable codes and regulations. In addition to the NEC requirements, there are also industry standards and best practices that should be followed when designing and installing electrical systems with generator backup power. These include recommendations for sizing conductors, selecting overcurrent protection devices, and performing regular maintenance and testing. Following these standards and best practices can help to ensure the safety and reliability of the electrical system. For example, it is important to properly size the conductors that connect the generator to the automatic transfer switch and to the load panels. The conductors must be sized to carry the full load current of the generator as well as any potential overload current. It is also important to select overcurrent protection devices that are properly sized and coordinated to protect the conductors and equipment from overcurrents and short circuits. Regular maintenance and testing of the generator and the electrical system are also essential. This includes inspecting the generator for any signs of damage or wear, testing the operation of the automatic transfer switch, and verifying the integrity of the grounding system. By performing these tasks on a regular basis, it is possible to identify and correct any potential problems before they lead to equipment failure or safety hazards. It's also useful to understand the different types of grounding systems that can be used in conjunction with generators. The most common type of grounding system is a solid grounding system, where the neutral is directly connected to ground. This type of grounding system provides a low impedance path for fault current and is typically used in systems with ground fault protection. Another type of grounding system is a high resistance grounding system, where a resistor is inserted between the neutral and ground. This type of grounding system limits the fault current and can reduce the risk of arc flash hazards. However, high resistance grounding systems are typically more complex and require specialized equipment. A third type of grounding system is an ungrounded system, where the neutral is not connected to ground. Ungrounded systems can offer some advantages in terms of reliability, as a single ground fault will not cause the system to trip. However, ungrounded systems can also be more difficult to troubleshoot and may not be suitable for all applications. The choice of grounding system will depend on the specific requirements of the application, including the size of the system, the type of loads being served, and the level of fault current protection required. Consulting with a qualified electrical engineer is essential to determine the most appropriate grounding system for a particular application. Furthermore, it's important to consider the impact of harmonics on the grounding system. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems in electrical systems, including overheating of conductors and equipment, increased neutral current, and nuisance tripping of circuit breakers. To mitigate the effects of harmonics, it is important to use harmonic filters or other mitigation techniques. It is also important to ensure that the neutral conductor is sized to carry the increased neutral current caused by harmonics. Finally, it's essential to document the grounding system and to provide clear labeling of all grounding conductors and equipment. This will help to ensure that the grounding system is properly maintained and that any future modifications are made in accordance with the applicable codes and standards. By following these guidelines, it is possible to design and install safe and reliable electrical systems with generator backup power. The information provided should be used as a general guide only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer and refer to the latest edition of the National Electrical Code for specific requirements and guidance. Moreover, specific project requirements need to be determined by calculations and engineering best practices.